This session is to discuss the linkage of river basin models with power pool or electric system models in the analysis needed for planning of river basins and electric systems at the power pool level within the Enhancing Climate Resilience for Africa's Infrastructure project. This brief introduction to the linkages of the models will require that you have listened to the sessions on each of the individual models themselves. What this session will do, we'll talk about how these models were linked to achieve the goals of the analysis. But I refer you to the sessions on the WEEP model and the sessions on the osmosis model, which will give you the details of those particular tools. In the ECRAI system, as mentioned in the introductory framework session, there were 4 steps that were undertaken. The step A was to look at a reference scenario, which is the current development plans of hydropower, irrigation, and thermal and other renewable electrical generation in the light of a current climate. Then it was to investigate that under the potential of 100 future climates, representing the uncertainty we are faced due to climate change uncertainty from emission uncertainty and scientific uncertainty about the nature of the changing climate to different greenhouse gas emissions. We will show in the next slide how the models were linked for this step A and step B in the analysis. What we see here are the tools that were used, the WEEP model and the osmosis model. The WEEP model had demands for hydropower at each of its new and potentially to be developed projects as well as existing projects. There was demands for irrigation. The model ran giving priority to irrigation, and then it attempted to produce the maximum amount of hydropower that it could within the system framework. This hydropower production was then passed to the osmosis model. You see that arrow on the right-hand side linking those 2 boxes. The osmosis model, which took forecasts of energy demands from the left with plans for thermal electric generation, and brought that energy generation into the osmosis model. Now, under climate change, if there was not the energy that was originally planned, there would be a shortage of available capacity and energy, and the osmosis model would have to make up this energy shortage by other sources of energy, and most of the time these would be at a higher cost, or particularly they would be at a higher fuel cost, as we would have to replace this short-term loss of hydropower with diesel generation or coal or other sources, which would mean more greenhouse gas emissions or additional costs due to the fuels. The osmosis model was an optimization model that will try to minimize the cost given the amount of hydro production. So therefore, we were able to run 100 climates through the WEEP model, and then WEEP would provide 100 scenarios of hydropower production to the energy model, and then we would estimate the economic costs of those and report them in terms of present value amounts. So this was the A and B, where we just passed what we called forward linkaging the hydropower to the energy model. Energy model had to live with the impacts that occurred, and we measured those in the A and B. Now, as we moved to the adaptation, we used the models in a different way. We would then bring in what we call perfect foresight, where we would say, how should we operate these models if we knew that this one of the 100 future climates was actually the climate? What would be our behavior? And we then looked at what kind of adaptations we could make from our current plans to minimize the impacts of climate. that were on us. And then finally, once we have completed this C analysis, we could then provide this information to decision makers so they could come up with a robust choice of their adaptations. So this required modification to the river basin model and then linkage of this modified river basin model to the osmosis model, which we will see in the next slide. So what happened here is the tool for adaptation, the water model, was now put in a framework of what's known as simulation-based optimization. So for each of the climate futures, what was asked of the model was to change the design of the hydropower and irrigation systems, with irrigation and food security being the highest priority, and adapting that by not building hydropower where the water was not there anymore, so that there would not be wasted assets or stranded assets, or in the case where there might be excess water, increasing the size of the hydropower systems to take advantage of these windfall gains of a wetter future. So that model would run to find out the optimal adaptations to the base PETA system. When that was completed, it would then pass its hydrologic production to the osmosis system. Now, when the osmosis system would receive this hydropower, in the past it would just run it. Now it would run it, give a change in the energy prices, and in such, it may be that certain activities in the water model, certain hydropower, now becomes economically feasible because the prices are higher, or vice versa. There is so much that the prices go down and other projects might not be there. So osmosis determines which hydropower projects should be retained, which should not be used. So you see this now a feedback loop on the right-hand side of prices for electricity, going from the osmosis model up to the WEAP optimization, and then the WEAP optimization would be run again. So how did this take place? Well, we have these two modeling systems, the osmosis, which is an optimization model, and now an optimization model of the water system, where we're trying to maintain food security, and within that, we're then trying to maximize the economic value of hydro production by adjusting the projects that have been planned. And so what we did was to go through a iterative scheme where we start off with WEAP taking the climate change impacts on the monthly hydro, passing that to the osmosis system in the orange box. Osmosis would run its model, optimize its values, come up with the levelized cost, and then it would pass these new prices to the WEAP model. WEAP would then optimize again, as I stated, because the energy prices could be higher than was expected in the first box or lower. WEAP would run and adjust it, pass those outputs to the osmosis system. Osmosis would run again, give one more set of prices. WEAP would run again, and that would pass it to the final adaptation run of osmosis. So we had 3 iterations in the system that was based on some preliminary work that was trading off between computer time and the convergence of the algorithm. So in most cases, we found that the model would converge in 3 steps within our tolerances, and this is the way it would run. Had there be more computer time or faster computers, we might have done 1 or 2 more steps, but for this study, a 3-step iteration was sufficient. So with that, we now were able to link the adaptations of both the energy systems and the water systems to these 100 plus futures. They were all there. So we have a design of the combined hydro water systems that now policymakers can look at and choose what is the most robust design we should take, given the fact that we don't know what the future climate is.